The broadcast is now starting. All attendees are in listen-only mode.
Okay, good afternoon, everybody. Sorry for being late. I was in another location. I just came running. So welcome to this, the FE7 review. Let's continue our discussion about the mechanics of materials. As all of you know, we are using the current edition of the reference handbook, the FE reference handbook 10.0, which is available online. You can download it from the NCEES. So this is the, sorry, last week I was committed to another event and there's something came up and I was not able to offer the class last Saturday. I think I added more sessions and an email also, I believe it was sent to you if I'm not mistaken. So today is 5/1/2021 and this is FE7. So I was busy helping the PE group. The exam was given last month, which is 4/22, 4/22, and 4/23. This is a PE exam was held, and another round of PE is gone. So right now the FE7. I'm still working on the book. By the way, now I can devote more time. Hopefully, I can assemble the 9 chapters, as I mentioned at the beginning, and put them in a form of a book. And some of you already emailed me in order to get the book. I said, the moment I'm done with it, I promise I will do it, and I will. So far, I send you 3 chapters. The statics chapter that we covered. I hope that you get a chance to go over the problems at the end of this chapter. Right now, we are in the mechanics of materials, which is very, very important chapter because a lot of other subjects will rely on the mechanics of materials. So this subject is very, very important. And let me see, I have the notes. Let me see, if I'm not mistaken. This is where we stopped last time. A sample problem 6.5, which is the reduction in area. And again, the equations are provided in the NCEES. So this is a mechanics of materials, and one of the expressions they provided to us, if you go a couple pages on page 4, obviously each chapter is numbered by its own number, it's not sequential order. So this is 4, page 4. So one equation is the percentage reduction in area. and is given by this equation here. The reduction area is equal the initial area minus the final area over the initial area times 100. So let me, one of you has a question for me or a comment or a suggestion. Let me see what's the comment or suggestion. One of you saying that cannot hear you. I wonder the audio from your end. I believe if anybody has an issue with the audio, let me click on the audio one more time. But do it, or you should be able to hear me. What about now? Can you hear right now? I believe this came from Ziad. Ziad, can you hear me right now? All indication from my end here, it says that the system is working, audio and video. Anybody else has an issue with the audio, by the way? It is okay? Okay, thank you very much. Okay, that means that you're from your end, Ziad, what you can do, you can just get out and join me again, or click on the audio a couple of times and make sure that your audio is working fine. Since one of you indicated that it's working, that means that maybe your system, and let me know, please. I hope that the system will be working fine. So I am on page 7 of the Mechanics of Materials, MOM, Mechanics of Materials, okay, handout or chapter, the one I sent it to you. So he gave you a steel rod is shown fixed from this end and free from the other end. And there is a load P acting at this point here, at point B, and the load or the force that is applied is 15 kips. Okay, the area of the AB is given, and the area of the BC is given also. So he gave you the cross-sectional area directly. Sometimes they give you the diameter, by the way, or the radius. Okay. So this is D1 and D2, for example. So all of us, we know the area is equal to by D1 squared divided by 4, or the by R1 squared divided by 4, by R square, sorry, by R square. Or the second is by D2 square over 4, if this is D2, or it is by R2 square. This is not 4 here, okay? So whatever dimension given to you, either radius or the diameter. So this is, assuming Poisson's ratio is 0.28. Poisson's ratio, they are using a Greek letter, by the way. Let me make sure that I'm using the same letter. Is new. This is new, Greek letter new. Okay, and Poisson's ratio, as indicated last time, is the ratio between two strains. The lateral strain over axial strain. And they put minus here because Poisson's ratio cannot be negative. So let me see if they give us Poisson's ratio or not. Yeah, here it is. This is the NCEES, all these equations, the one I put in a box. So Poisson's ratio is new. Poisson's ratio is the lateral strain over the longitudinal strain or axial strain. And here is a minus sign, by the way. So, and the reason they put the minus sign to ensure that Poisson's ratio is positive quantity. And at the end, by the way, at the end of the, I'm providing you with the table, or the two tables. These two tables are provided in the NCEES, table 1 and table 2. Table 1 is the typical material properties, okay? And one of them is Poisson's ratio. So this column here is representing the Poisson's ratio, and they are using the Greek letter nu. And Poisson's ratio for steel is 0.28, sometimes 0.3. Here it is, he put it 0.3. Aluminum 0.33, wood for Douglas fair, mean Douglas fair, and so on. So you don't have to memorize them. They are listed here. The same table, by the way, since I am talking about this table, and this is the table that material properties, if you have the NCEES document, which I highly recommend either to purchase it or to download. And if you go to mechanics of materials, this is the mechanics of materials chapter. Let me go to mechanics of materials here. This material science. This is statics, dynamics, and mechanics of materials. I think it was after dynamics. Yes. Yeah, here it is. So this is on page, by the way, 130. If you have the original document with you, this is 130, page 130, page 130 of the NCEES reference book. So this is mechanics of materials, and this is where I extracted the information or the equations and the tables and the charts and so on, and I put it in boxes in my handout. At the end of this, you will find there are two tables, as we indicated last time. I'm sorry that I'm repeating some stuff because some of you are attending the first time, so I have to bring everybody up to speed. So material properties, and this is specifically on page 138. And this book is your responsibility to download it from the ncees.org. You can go to the ncees.org, and I'm sure that all of you are familiar with this. And after you subscribe with them, you will be able to download this document. And also they sell it, as far as I know. They sell it. You are very welcome to either to download or to purchase it. It is your choice. So the first table is table 1, and this is what I was talking about. The table I showed to you in my material, it is the same as given here. And Poisson's ratio is, as you can see, it is by far less than 0.5 because we do have an equation I showed to you last time. So Poisson's ratio, this Greek letter nu, it is the axial over the, the lateral over the axial, and we put a negative sign to so nu, it is, we take normally the absolute value, by the way, sometimes we put it that way, or as given in the reference book, it is a negative. The lateral strain over the axial strain, or as given, it is the axial strain, because any material, okay, you apply a tension. So if you have 2 marks, normally this we do this in the lab by bunching 2 dots on the specimen. This is a tension specimen, for example, where with the center bunch, for those of you who took mechanics of materials lab, they are familiar with that. We make a little tiny dent here and dent here, and the distance between is 2 inches. Okay, it's called the gauge length. Okay, so you'll find that there is a reduction in the cross-sectional area. This is getting skinnier and skinnier until ultimately it will fail, like the specimen I showed you last time. This is after the failure. This is how it looks like after the complete tension test. So as you can see, the reduction in area, this is what we are looking for. So the strain along this, we call it axial strain, and the other strain is, which is perpendicular to it, they call it the longitudinal strain, or a transverse. Sometimes we call it the transverse, or a longitudinal strain. As, let me see what they are using. They are using the so this is the lateral axial strain. This is the lateral strain, and the axial strain, they call it longitudinal. This is longitudinal strain. So there are two types of strain, one in the direction of the load and one is perpendicular to the load. Okay, so if this is epsilon axial and this is epsilon lateral, let us use the term lateral strain as they use it in the NCEES. So instead of axial, you can say that this is a longitudinal strain. And by far, by the way, this axial strain is much, much bigger than the lateral strain. And this is why Poisson's ratio, it is for most of between 1/3 and 1/6. Okay, so 1/3 and 1/6, and it cannot be even 0.5 because Poisson's ratio is, for example, E steel, the one I showed to you, is 0.3, E aluminum is equal 0.33, and so on. Okay, so and nobody will ask you to memorize these things because they are in the book. So, but I'm showing you the table where the table is located. So Poisson's ratio, lateral strain over axial, which is longitudinal strain. Okay, so longitudinal strain is the same as axial strain. So if Poisson's ratio is given, what is the percentage reduction in area, okay, of the portion AB? So he's looking about this portion of the shaft. What will be the reduction in the area of this? So let me look. Oh, here is another hand. Okay, somebody have a question. I will send it to you. Okay, Brian is asking, can I? Yes, I will send it to you after I finish the class today. I cannot send it right now. Okay, so hang with me until probably the break. During the break, probably I can do it during the break. As long as you send me you email me. If you email me info@pespe.com, I will try to see if I can jump on the other computer. info@pespe.com. I will be glad to respond to your email. I know I can get your email from the other location, which is when you enroll in the class, but if you can send an email very quick, info@pespe.com, I will respond back and I will attach the mechanics of materials chapter. So the solution, and again, the four answers provided here, and the percentage reduction in area normally expressed as a percent. This equation is very important. Delta is equal PL over EE, and I talked about this, and this is only within the elastic range. And this came from Poisson, from the modulus of elasticity E. E is equal sigma over epsilon, as we indicated last time. So if E is equal sigma, sigma is equal P over A, and epsilon is equal delta over L. If you solve for delta, delta is equal PL over AE. So this is the equation that we are going to use it in different chapters, by the way. So step number one, this elastic longitudinal deformation delta, and engineering strain is delta L over L. Okay, so if I know delta and I know L, so I divided by the original length. The original length is given to me. Sorry, the allergies start to bother me a little bit. The definition that we are using, the engineering definition, there are two definitions for each, by the way, and probably I can remind you again, and they mentioned. So when we're talking about stress, which is sigma, there are two definitions I needed to be aware of. One is called the true stress, and one is called engineering stress. And the same story with the strain. Epsilon, also there is a true and there is engineering. The true definition for stress is equal B over A sub O. This is the original cross-sectional area. But the engineering stress is B over A, where A is called instantaneous area. Instantaneous, some books they put it IN, INST, instantaneous, because as we apply the tension to this specimen, the diameter is getting smaller and smaller. So the initial, when we measure the diameter at the beginning using a micrometer or a caliper, if you remember this from school, normally we give the student this specimen or the other specimen, and I give them a micrometer or a caliper to measure the diameter, because we cannot measure the area. We can calculate the area, the pi d square over 4, or lowercase or uppercase is not a big deal, or the pi r square, as all of you know. So basically we measure the diameter, or from the diameter we can get the radius, which is half of the diameter, and then this. So the area can be calculated, not measured. We measure the area when we are going to talk about surveying. Surveying, we are going to talk about the one section is called the surveying. This is just on the side. We are going to use one equation, which is a volume of the using the average in the area, which is A1 plus A2 divided by 2 times L, and we divide by 27 to convert it. This is coming later on in the subject of the surveying. I believe it is given, if I'm not mistaken, let's go to the civil section, because as you know, the civil section started on page 258, and you need to be familiar with this book very well, and you know exactly how to search using the PDF copy, because basically the screen, as all of you know, the screen on the actual exam, when you go to Pearson web testing site, the screen will be divided in 2 sides, as far as I know, or 2 sections. One side you have the reference book here, a reference book, which is the information in front of you. Okay, and this is a PDF. You need to search. Okay, and I highly recommend you to download the PDF and try to search, looking for Poisson's ratio, looking for whatever, and the questions will be here on the other side, and so on. So on page 258 of the NCEES, everything reference to NCEES 10.0, starting with the civil, okay, engineering section. Okay, so there are some subjects before that. This is the general, like statics, dynamics, mechanics of materials, economics, or all these subjects that are shared by other disciplines. But when they come to each discipline, because it's one book, it does have the mechanical and civil and electrical and so on. So the civil started on page 258, please. So we are going to see one section here. Let me see if I can locate it, which is the average in the area method, which is after the transportation, all this steel design, hydraulics, hydrology, open channel, and we are getting very close. We're supposed to be on the following page. If I remember, here we go. Here it is. Probably I mentioned it, okay, before. So this is on page 307. 307. So this is the equation. Here it is. It's called average in the area method, which is the earthwork formula, which is volume. Here it is. They write it this way: L times A1 plus A2 divided by 2. They did not put 27. Okay, so this is the volume of the earthwork. So I said that we cannot measure the area. So how would they get the area 1 and the area 2 here? Okay, this case we are the cross section will be given to you. The cross section will be given to you like this. For example, if this is a fill section, this is OG, the original ground, as we're going to see, and this is a fill section. Okay, this is called embankment or fill. So this is A1, and at a distance from this we have another area. It's called A2, and they are separated by a distance L. So this is the area A2. When you plot the cross section of the road or the street or whatever facility you are designing, so this area here, we can measure it. How we measure it? There are more than one method. I will talk about it, but basically if the cross section is given to you, you can approximate it by calculating the areas. For example, and I have some sample problems, show it to you. So if the depth of the fill is known and the side slopes are known, and I know the width of the road here, so basically this is the area of a trapezoid area is equal this width W1 and this at the bottom is W2. And the depth is D, so the area is equal W1 plus W2 divided by 12 times the depth, the area of a trapezoid. We know this from high school. So the area always is calculated. We measure the area sometimes using something called a planimeter. It's a very old measuring device. I will show it to you because I discussed this in depth with the surveying for the PE. So these things, okay. So we're going to see the average in the area, and they came up with another method. It's called the Prismodial formula, which I mentioned this for some reason. I wrote it here. This is on page 307 again of the. So the area cannot be measured, but the area can be calculated, except if you are using a planimeter. But for the case of this, for the case of a rod like this, no, you have to get the diameter, and after that, this is the engineering definition for the stress and the true definition. So they use the instantaneous area, or the area at the moment that we collected the value of the P. The strain, it is the same thing, a true strain and the engineering strain. The true strain is delta L over L sub O, or the deformation, some books they call it elongation over L sub O. So again, the original, no, so let me reverse it. Sorry. Let me reverse it. I reverse the true with the engineering. Sorry. Okay. Normally I start with the engineering. That's why blindly I said. Okay. So let us make this correction. So the true is the instantaneous. Sorry, instantaneous, and this is the A sub O, and this the true is the delta L over L, with L is instantaneous. This is delta L over L sub O, or the elongation over L sub O. So the engineering is dealing with the initial, initial area, or the initial length, the initial, okay, the initial. And you will see this, I believe it's mentioned also in the NCEES. So there are two definitions. Obviously, this is much easier to deal with, the engineering. It's easier to measure the original diameter, and from the original diameter, we can get the original cross-sectional area. And the same story with the engineering strain, which is epsilon. So I needed to be aware of that. So the engineering strain is equal delta L over L sub O, here it is. So we plug it, and we can solve for the lateral strain, and the final diameter is equal the original diameter minus the reduction in the diameter. So we can plug it here, and after that we apply the equation, which this equation is given the percent reduction in area is equal the initial area minus the final area divided by the initial area, which we can express as in terms of the diameter, okay, because we can take the pi square, pi outside, by d square over 4. We can factor it out, as you know, and we ended with this. So it's a very good problem. I know, if you remember, as I mentioned before, you have a very limited amount of time. So the following page, let me use another copy, because this copy, it seems this is the copy I was using to check. This is on page 8 of my, and sorry, I have to go a little bit fast. Page 8, yes, to try to wrap up this chapter, and after that we'll jump in the materials chapter. Materials also, it has a lot of discussion. The shear strain, they are using the Greek letter gamma, and this is from the torsion test, which is tau divided by G. G is the shear modulus, and tau is the shear stress. Modulus of elasticity and G, they are related by this equation, and this equation is given in the NCEES. If you remember the equation that I showed to you last time, and here it is. This is the NCEES equation. G is equal E divided by 2 times 1 plus nu, and this is the new Poisson's ratio, the one we talked about. Okay. I need you to know that G is about 40% of E. G is equal about 40% of E. If we take Poisson's ratio as an average value of 0.25, you will get this is about 40%. Because G, which is a shear modulus, we get it from the torsion test. Sometimes we don't have the capability of doing the torsion test. And if you look to the tabulated values, by the way, of the NCEES table at the end, I showed you one table, table 1. It does have the modulus of elasticity. Here it is. Okay, this is a table 1 on page 138. Please keep this book side by side. Keep this next to you, the NCEES book, because I will refer to it a lot. Yes, I do have all the information. I have it in my document, but I always prefer to go to the original document just because I need you to see where it is and where it is located, because this is what you are going to see in front of you on the computer. So this is the modulus of elasticity E. Modulus of elasticity, and in MPSI, M stands for mega. Mega is 10 to the 6. And mega PSI. And the one next to it is GPA. GPA, this is giga. Giga is 10 to the 9. And Pascal PA, which is Newton per meter square. So gigapascal, we know Pascal is Newton per meter square. So we need, okay, for example, for steel, we are using 29 million PSI or 200 gigapascal for steel, for example. If you look to the G, which is the one next to it, this is a shear modulus, also mega and the gigapascal. You will find this 11.5 and this is 29. So if you take 11.5 and if you divide it by 29, this will give you an indication, the percentage I'm talking about, which is about 40%. So the G over E is about, okay, 2/5 or is about, okay, 0.4. So G is for a steel example, for example, 11.5 as given in the table, 11.5 10 to the 6. And the modulus of elasticity 29 times 10 to the 6. So this will give you something in the neighborhood of, if I have a calculator, I believe I do have one here. It should be in the neighborhood of this number. And normally we use it about 0.3966, which is about. So if you don't have a testing facility or testing capability to determine the G, which is the shear modulus, in this case, we use the relationship between G and E to get the G from E, which is about 40%. About. I say about because Poisson's ratio is not constant, is variable. Poisson's ratio, here it is. So this is the equation, the lateral strain over longitudinal strain. Longitudinal strain, as I told you, is the same as axial strain. And the minus is not a typo, is always, we proceeded this with the minus to ensure that Poisson's ratio is a positive quantity, okay? And I gave you, here it is, Poisson's ratio. For most of the structural materials, that it is between 1/3 and 1/6. Okay, so this is, for example, steel, aluminum, copper. I give you some examples here. For most structural materials, normally I teach this in the materials and the concrete lab for those who are attending Fresno State 121L and 124. Question number, okay, 6. We need to understand, or to be ready, by the way, with conceptual questions and with calculations, okay, because the materials, okay, it does have, or the exam, it does have both. And already I showed you this before, but this is the NCEES, the book they sell on their website. this one here. This is, you can order directly from their website. Okay, the FE Civil practice exam. They have practice exams for each discipline. So for the FE Civil, I highly recommend you to buy this directly from them. This, it does have 100 problems. This is, okay, 100 problems. And we need to be ready. For example, this is a problem similar to one of the problems that we solved. This is problem number 18, is asking the magnitude in Newton, N stands for Newton, okay, of the resultant of the three forces, coplanar forces. Coplanar forces mean 2D system, 2D as we talked about before. Y. This is 2D, which is X and Y, so this is X and Y. They give you the force A and force B and force C, and all the magnitude and the directions are given for each force. This is 5 Newton, this is 2.12 Newton, and this is 2.12 Newton. As you can see, he give you two. They are identical, so not to confuse you, but you have to be careful. Okay. And the angle here is 105. So, so we talked about this, the resultant. We talked about it, and he's asking only for the magnitude, by the way. Magnitude. Sometimes they ask for the magnitude and the direction. And the direction as we solved before, and we have equation for the direction, which is the angle theta and so on. So, so I needed to be aware of that. Also, sometimes they give you something like problem number 19 of the NCEES, okay? That a heavy roller is held in equilibrium on a frictionless plane, frictionless plane AB. So here it is. So that means that the friction force between the roller and this plane is ignored because it's a frictionless. And this is the external force F, which diagram correctly shows a vector polygon of the force acting on the roller. So we do have the force polygon, okay? We do have external force F, and we have a reaction, which we'll call it normal force, okay? And since he said that the friction is going to be ignored because this plane AB is a frictionless, so obviously there is no friction force. When we talked about the friction, friction force is going to be ignored in this case because he said so. So there is no need to consider the friction force. So he gave you 3 diagrams, okay? Sorry, 4 diagrams, option A and option B and option C. So we need to select what is the appropriate one. So what do you think? Which one is, okay? So, okay, so this is friction and this is the normal force, okay? Does this roller has a weight, W? Yes, acting down, W. W is equal mg, and this is the normal force. So in this case, I have 1, 2, 3. So we do have this is F. Obviously, but the process of elimination, by the way, I needed to learn this, is called the process of elimination. Process of elimination. Always I stress it with the PE group and seismic and surveying. Also, this morning we were talking about the seismic, this morning with the PE seismic group. So the process of elimination is very powerful, and we need to learn this process. If you look to the given force is given this direction here. So I have 1 is parallel to it. This force here is going out. So this is out. This force here, the direction has a change. So this is out. This force here is going this way, so this is out. Okay, okay. Or maybe he used this to represent this. I have no problem with that. If you go with this, so this is F, and this is F, that's fine. But you will find the other two forces, okay? One is up and one to the right. Okay, where is the weight? Where is, okay, if you remember when you talk about friction, let's take the one that it is horizontal plane. Horizontal plane, we have external force F, and we have the W, which is equal mg, and the normal force N. If we ignored the friction, so force, there is no F here, the friction force normally we use, okay, like this, we use lowercase f, which is mu n, if you remember mu n, where mu is a coefficient of friction and the n is the normal force. So this is gone for in our condition here, or our case here, so there is no but he gave you this is as inclined plane like this. So this is the rotor, or the, so it does have W, which is equal mg. Okay, the normal force, okay, is always perpendicular, okay, to the contact surface, normal force, N. Okay, this angle must be 90 degrees. Okay, and the external force that's given, this is F. So this is the three forces, or the three components that it should form this polygon, vector polygon. So you can look to these. So if you consider this and this and this is external force, I have no problem with that. So this is out. But if you look to the other two, you will find that by the process of elimination, the only diagram is this one here, where this is the W, this is the W, and this is N, the normal force. And as you can see here, he put one up, okay, one down. Okay, but look to the arrows, okay, this here. So we need to do this, and always a free body diagram. Always I encourage everybody free body diagram, or so the process of elimination. Can I say, oh, this it cannot be, and so on, and we will learn this. If you look to this problem here, problem number 20, select the location in which on the x-axis. So this is x and this is a y, where an additional load must be applied or must be placed in order to achieve equilibrium of the L-shaped bar. Okay, so we need to place a force in the x direction, or the x-axis as he indicated, in order to achieve equilibrium. Equilibrium means that the sum of the forces in the x direction must be zero. This is what is equilibrium is. The definition of equilibrium, one of the equilibrium equations that we talked about. So, and the second equation, sigma of force y is equal 0. So, this force, it's inclined force. And as I mentioned, there are two rules when you are dealing with inclined forces. Any inclined force, break it down into components. So this, it could be in the x component and in the y component. So this here is 10 divided by, this is 5. Because the slope, he give you 3, 4, 5. I divide by 5 and multiply by the x direction, which is 3, the horizontal one. And the y component is equal 10 divided by 5. They again divide times 4. So this here is 6 pounds. And this is equal to 8 pounds. Okay, this is gone right now. So right now, I do have in the X direction, and you have to do this very quick, by the way, because as all of you know, you have 110 questions in 5.5 hours. So it is, so you have very limited, so 110 questions, as all of you know. Okay, and they give you 5.5 hours, and also check with the NCEES if they have any change. So I have 6 bounds going to the right, and I have 8 bounds going to, I have here 6, and I have 6 here. Okay, so they are balancing each other. Is this correct? Okay, in other X components, so the component of this force along the X direction is 6 and 6. So they are equilibrium, 6 to the right and 6 to the left. But if you look to this, I have 6 going up and 10 going down, and the component which is 8. Which is 8. Okay? Okay, so I have 8 up and 6 up is 14. So in this direction, I have 14. Is this correct? I have 10 going down, 10. Balance. So in order to satisfy the second equation, because the first equation is done, the sigma force X. Okay, 6 to the right and 6 to the left, they will cancel out and we end it with 0. So equilibrium has been achieved. But if you look to the Y components, I have 8 up, 6 up, and 10. So I must have additional 4 bounds. Oops, 4, not 14. 4 acting down. Are you with me? So this 4 bounds should be acting somewhere. And he wants us to see it should be acting here or acting here or acting here in order to create or achieve equilibrium. The third equation is going to help us, which is sigma moment equals 0. So the moment, and the moment is force time distance. So if I sum moment here, sigma moment, I know there are 4 bounds has to be down, but I don't know how far from here to here. And I call this distance x. So if you sum moment about O for all forces, you'll find the 6 has no moment. This 6 has a moment. And this 10 has a moment. This 8 has a moment. This 6 has no moment. This 4 has a moment, which I need to locate how far from the origin here or the. So by summing moment became piece of cake. Okay. So let me do it very quick for you here. So sigma moment about O is equal 0, this point here. And you need to assume a direction, by the way. Clockwise or counterclockwise is up to you. And this must be equal 0. So if I put my finger here, you will find that 6 has no moment because go through moment, as all of us know. We discussed this moment is equal force time distance. So the 6 has no arm, but the 10 has an arm. So it is 6 times how far from here to here is 5 units. And the question is positive or negative according to my sign convention. No, this is negative because so is negative. I'm done with this. Don't forget the force, by the way. This is a common mistake that sometimes we'll forget. Let's look to the 10. 10, it has 1, 2, 3 units. So it is 10 times how many units? 3. Positive or negative? No, this is the same direction, so it is positive. I am done with that. Okay, the 6 has no moment because go through. So I have the 8. So it is 8 times how far from here to here? This 8 and this is 6. And is this positive or negative? It's going to be negative because counterclockwise. And I still have the 4. It should acting down. So it is positive. Plus 4 times x equals 0. This is the equation that we need to solve for x. Okay? And probably he will give you a diagram showing the location of the x, where the x should be, and you select the proper diagram. So the 3 equilibrium equations we talked about this before. So there's the centroids are very important. This we will cover it on the math, by the way, section, where we can calculate the centroid for an area. The centroid for an area. The distance from the y-axis to the centroid of this area, which is this here, measured to the y-axis. And we are going to see this. This, for example, the moment of inertia. Okay. The moment of inertia, and this is to the 4th power, because we know it is Ix, for example, is y squared dA, the moment of inertia, or the Iy is equal to x squared dA, as you know, so it is a 4th power, okay, of the area about x bar. So here it is, x bar. And here C stands for centroid. Do you remember the theory we talked about last time or the time before, which is the parallel axis theorem? Very important. Parallel axis theorem. Because this is a centroid. We call this is the XC, and we call this is YC. So the 2 axes, they go through the centroid, you call them centroidal axes. The parallel axis theorem, it says that the moment of inertia Ix bar, which is this one here, is equal to the Ixc, which is the moment of inertia about the centroidal axis, which is in this case the x, plus the area or the dimension dy squared times a, where a is the area. What is dy? Dy is the distance from here to here. The distance from the centroidal axis to the axis we are interested in. The area, this is area of a trapezoid, 3 plus 6 divided by 2 times. So the first thing that I need you to think about, how can I get the Ixc, which is the moment of inertia about the centroidal axis. Centroidal axis, x in this case, Ixc. The tables are provided at the end of this section, the statics. You will find the answer. So you don't have to derive it from scratch. So before the dynamics, there is the static section. And let me see if they provide one. Yes, they did. Here it is. So what they did, this is on page 111, please. Again, this is what they are referring to. So they give you this trapezoidal area, and here is a centroid. This is the area which this plus this divided by 2 times h. And he is talking about the Ixc. Here it is. What is the Ixc? Okay. Ixc is this one here. This is xc. So this is, so it's given to you. H is given, and A is given, and B is given. It's just a matter of plugging this number into this equation. So we need to be aware of that. Where can we find the information is a very important to know where are the equations, where they are located, and after getting the Ixc, we are using the parallel axis theorem, which is also is mentioned, if you remember. Where is a parallel axis theorem, which is a moment of inertia? And here it is. On the previous page, here it is. The moment of inertia, parallel axis theorem. It is Ix is equal Ixc plus dy square A. So they are saying that this is xc, as I explained. And I need to get the moment of inertia about the x-axis. There are two requirements here, by the way. If you look to my notes, you'll find there are two requirements. This must be known. This is the first requirement. So the moment of inertia about the centroidal axis, this we call it centroidal axis. Centroidal axis. This is the first requirement, that this must be known. The other requirement, these two axes must be parallel. And this is the dimension dy in the equation. So the parallel axis theorem is important, and I need you to be aware of that, okay? Problem number 24, for example, in the figure below, the coefficient of static friction between the block and the inclined plane is given. So mu is equal 0.25. And mu sub s, by the way, because with the coefficient of friction, there are two of them, mu sub k and mu sub s. Okay, mu sub k is larger than mu sub k, by the way. This is called the static coefficient of friction, and k is called kinetic coefficient of friction. They give you the static coefficient of friction. And this is a block here, placed on this inclined plane. An inclined plane, as you can see, is raised. The block will start to begin to slide when. So as we move this or raise this, and this is the angle phi. And we talked about this. It's very easy. So there are some questions are, as far as the time, it takes very small amount of time, maybe a minute or less, okay, which is the tan phi, by the way, the tan phi. Okay, so tan phi is equal mu, by the way. Okay, and this way, say phi is equal inverse tan of mu. Of this number here, which is 0.25. So when tan phi is equal 0.25, and we can derive this, by the way, when we have this block here, if you remember in school. So this block here is at inclined plane phi. So we have W, the one W is equal mg, and we do have a normal force. Always normal force N is perpendicular to the contact surface. And this angle, by the way, is also phi. The angle between the weight and the normal force is also phi, equivalent to this one here. And this block is trying to slide this way, down, along this. So I have a friction force F. Always F is opposing the motion. F is equal mu N. When this block start to move, called impending motion. It's called impending motion. So I used to do this back in Las Cruces, New Mexico. The block I showed you last time, and I used to have the block and I used to have the plane and raise it up. And so we need to be aware of that. All these things are very important, okay? So let us be aware of all these. As far as the mechanics of materials, where is the starting? Okay. Yeah, here it is. This is the first question in the mechanics of materials, question number 30. We'll go over these. Okay, more circle. If we decided to go to use more circle, and this here, question number 34. 34, given the stress strain curve, which material has the largest plastic deformation? Plastic deformation. Plastic deformation. In a stress strain curve, which you are going to see a lot of samples today, this is epsilon and this is sigma, which is B over A, and this is delta L over L. And as I told you, when we develop this stress strain curve, we are dealing with the engineering definitions. It's much easier to measure in the, or to perform it in the lab and measure also in the lab. So we are dealing with the original A sub O and L sub O, which is the engineering definitions, engineering. But sometimes we write it as epsilon delta L over L, and we know this is the engineering definition. Because we measure the diameter once and that's it, okay? Because if you like to do the true stress and the true strain, you have to be continuously measuring the diameter during the process of testing, and this is not really convenient. And this is one reason. The main reason, by the way, that the true and the engineering are essentially the same during the elastic stage. So we have a linear portion, and the slope, as all of you know, slope E is equal sigma over epsilon. Or some book they brought the delta sigma over delta epsilon. Change of stress over change of strain. This is Hooke's law. Do you remember Professor Hooke? Okay, it's called Hooke's law. Hooke's law. So after the linear portion, you'll find that the material goes a little bit up and come down and go straight like this and start to go up again, and it will fail somewhere here. So this stress strain curve is divided into sections. This is the elastic. And they call it elastic because like rubber band, like when you have a rubber band, if you are applying force and you release the force, the rubber band will go back again to its original dimension or original shape because it's elastic. All of us, we know that. So this is the rubber band, and you apply a force. You are pulling this with a force. If you release it, it will go back again. So it is elastic. So if you load the specimen and unload, it will go back again to zero here. There is no permanent deformation or permanent set, as we call it. After that, after the elastic, it will go to the plastic. A plastic. And after that will go what's known as the strain hardening range. So this, almost the horizontal line, because we ignore, by the way, the upper, and we are dealing with the lower yield point. Elastic, plastic, and the strain hardening. So if you look to the material B as in boy, you will find that this material goes straight, okay, up to this. This is called elastic limit or proportional limit. This is strain, by the way, which is epsilon, and this stress is sigma. So we need to be familiar with the shape of the stress strain curve for the brittle materials and ductile materials. I will talk about this today also. Okay, so after the end of the elastic stage, this is a plastic stage. A plastic, which is, as you can see, all of them, they don't have this amount of plastic, okay, stage. So obviously material B is the one that has the largest. Pay attention to keywords. keywords. Keyword or keywords, normally every question, okay, it does have a keyword. In the past, I used to write questions to the PE and the FE and all these things. So normally when we write these questions, obviously this is way back, I am out right now, legally I am out. So when we write questions, normally we select certain keywords or keyword or words, more than one word or just only. So this material here goes straight and it fell up to here. This here is non-linear, by the way. This like steel is a very good example for steel, like this one here. This is for A36 steel. This material and this material here, this is like concrete, okay? It does have non-linear, so it's a brittle material. This is a brittle material, like concrete, as we're going to see in the material section, a brittle. This is steel is a ductile material, ductile or ductile, as the British they pronounce it. So we need to pay attention to these things, okay? This is also, I believe, okay, 35. This one here, okay, which of the following is true about circular shaft is subjected to a torsion only? Torsion, okay? So we need to be ready for conceptual questions like this one here. We're going to go over it, but this is a question number 36. Torsion, okay, for a circular shaft. He didn't say circular shaft solid or circular shaft hollow, because we do have both H-O-L-L-O-W, hollow, okay? So a circular solid shaft like this, or a hollow shaft like this. Let me try to draw. This is like a circle. I know in your end it may be like an egg, but believe me, this is a circle. I try to draw a circle because the camera is a little bit, okay. So this is a hollow shaft. So we are going to see the torsion equation, tau is equal TR divided by J, where R is the radius. You will find that the shear stress, tau, varies linearly from the center all the way to the maximum. Is like this. So 0 at the center. Why? Because R is equal 0 at the center, and R start to increase all the way, or the distance start to increase all the way until we get the maximum, which is the radius in this case, TR divided by J. So that the maximum shear stress occurs at the outer fibers. The maximum shear stress occurs at the center of the shaft. Center of the shaft is equal 0. Okay. The constant shear stress occurs throughout the shaft. No shear stress is present through the shaft. Again, a process of elimination. A process of elimination. Try to get the right spelling here. Okay. Very important, but you will not be able to master or to use the process of elimination unless you study and know exactly what's going on. For example, he said that no shear stress is present through the shaft. This is not true statement, okay? Because we know any shaft subjected to torque, which is like this. This is what we do in the lab. This is the shaft like this. Here it is. And I'm sure that you did the torsion test in the lab and apply a torque T. So this will become originally it's a straight line. And because of this point is going to move to here. This is A, and this is what you remember from. So there must be a shear stress. How you apply a torque without it causing a stress. So this is out, a process of elimination. He said that constant. I know the constant means that the shear stress is like this. This is what's called constant shear stress. Okay. So This is, by the way, this is a tau max, by the way, tau max. To be more specific, so this is a tau max, here it is. Because we are going to see another equation as the radius increasing from 0 all the way to the maximum, sometimes we use rho, sometimes we use y, distance rho, or y, it depends on the book. I will see what equation they are using, but the maximum shear stress. The same story for the hollow shaft, by the way. If you look to the hollow shaft, also the stress is linearly. This question here is missing one. If I'm going to write this question, probably I will add another statement to it. Because this is true and this is true for the solid shaft and for the hollow shaft, as long as we stay within the elastic range. So this is only within the elastic range. Because if we exceed the elastic range or elastic stage, the shape of this distribution is going to vary, by the way, and it could be constant. And when we have a fully plastic, I will show you this fully plastic, you will find the shear stress is going to be uniform. This is why constant throughout the shaft. This is true statement. If you have a fully plastic, he didn't mention that because he expected that you are going to pick the answer A, that the maximum shear stress occurs at the outer fibers. So this will be the best, but to be 100% right without really causing any confusion, the word within the elastic range or elasticity should be added here into this statement in order to make it 100%, because maybe some of you thinking that maybe the shaft will go through the plastic, which I will show to you when I draw these diagrams. Okay, number 37 here is starting the materials. Materials, the chapter of the material, okay. They have good section about concrete mix design. I will show you how to design a mix. And there is no need for you to go and buy concrete from out source or any ready mix plant. You can mix your concrete at home and have fun. I will show you that. Okay. So he's talking about ready mix concrete being delivered at the job site, and it's found that has a slum less than the specified amount, without compromising the strength. Which of the following is the most appropriate corrective action? A slum. We do have something is called Slum Test for those who took the concrete lab. It is a cone like this. It is 4-inch in diameter at the top and 8-inch at the bottom and 12-inch in height. Okay, and we fill this cone in 3 equal volumes, and we tap each layer 25 times and we lift it up. In fact, in my book, I believe, if I'm not mistaken, on this chapter, I added a picture for a slum because I needed to, let me see if I have it here. I used to have a picture. This is illustration here. This is in the chapter of the materials. We'll see it. And I don't know if I have a picture. I used to have, because I took this from my. Yeah, here it is. Here it is. This is so I included. So testing of concrete. This is the slum cone, and I'm sure that we fill it in the 3 and lift it up. So this it has a 0 slum. Okay, this is the distance from here to here. We call it slum. We don't like to have the mix that is really very harsh mix or very soupy mix. This is, for example, collapse if there is too much water. Okay, so this is not acceptable. This is called shear. If the cone shear like this, is a true slump where you lift it up between 5 to 7 seconds. You will find that This cone has two handles, as you can see here. It is two handles, and lift it up, and this is how we run it, damping rod, and we are going removing and so on. So this slum is specified by the ACI code. Okay, the American Concrete Institute, they came up with what is the acceptable range: 2 inches, 3 inches, 1.5 inch, and so on. Because slum is indication of something is called, by the way, we call it workability, and we'll see what's the definition of it. So we don't like to have a mix that's very stiff mix, and also at the same time we don't not like to have a soupy mix. So we will see that. Okay, so let me stop here and let's go back again to the mechanics of materials. I'm trying to give you a taste of the type of problems that you might see on the exam based on the NCEES. I hope that the problems on the actual exam will be represented or reflecting the difficulty of the problems in this book here. I call it the white book, okay, the NCEES. They provide only 100 questions, but the actual exam, if I remember correctly, they mentioned that you must have, or they should have, they give you 110, okay? How they grade the exam, don't worry. I know this scoring issue is an issue, but don't worry. Just study hard and prepare yourself and pray to God that you will be passing from the first time and forget it, and after that you can move to the second phase. Okay, so I am on page 8, problem 6-6 of the mechanics of Poisson's ratio. Which of the following is true? Poisson's ratio is the ratio of the lateral strain to the axial strain. Poisson's ratio never exceeds 0.5. Poisson's ratio is always a positive quantity, and all of the above. The answer is all of the above. Okay, in fact, Poisson's ratio never exceeds 0.5 because we do have something is called bulk modulus. I don't know if it's K is equal to, I don't know if I have it here or not. I will show it to you. K is called bulk modulus. Bulk modulus. And it cannot be exceeding, and I will remind you when I hit the equation, okay, to save time. So Poisson's ratio is the ratio between the lateral strain to the axial. Axial, as I told you, they call it longitudinal, is another name. So, and never exceed 0.5. If you look to problem 6-7, I have too many problems, by the way, so I'm not going to go over every one of these. Okay, so, but, okay. A circular aluminum rod 10 millimeter in diameter is loaded with an axial force of 2 kilonewton. Assuming most of elasticity is given, giga Newton per meter square. What's Newton per meter square? It's PA, Pascal, sorry. Not Pascal. Pascal is Newton per meter square. Okay, I needed to know that. And Poisson's ratio is given. What is the decrease in the diameter? Very interesting problem. Okay, here it is. Stuff that we talked about before. Go over it, and if you have any issue, please let me know. If you find a typo or a mistake, since this is the first draft, so probably, okay, if you find a typo or a mistake or an error, let me know. I will be glad to go over it, okay? Problem 6-8, shear modulus. Shear modulus, by the way, is G, okay, which is the one we get it from the torsion test. Which of the following is true? Shear modulus is the same as the modulus of elasticity. No. We said that G is about 40% or 0.4 of E, the one I showed you. Shear modulus is always a smaller quantity compared to modulus of elasticity. That's correct statement. Okay. Shear modulus can be determined from the uniaxial testing. No, this is from torsion. From the torsion test. And we plot, by the way, this is torque, and we locate what is the angle of twist theta, and we plot a curve, okay, T versus theta, theta over L, by the way. We call it theta over L, which is called unit detrusion, if you remember this unit detrusion. It depends which school did you go to, but anyhow, and the slope of this line is G, by the way. Okay, shear modulus is the ratio between the shear strain and the shear stress. Shear strain, they are using gamma, and shear stress is tau. So G is equal tau divided by gamma. Here he reversing it. Shear modulus, which is G, is the ratio of the shear strain, which is gamma, over the shear stress. Now, it is the opposite. So the answer is, so the only answer is correct is D, as in doctor, and here it is. If you flip the page, you will find, oh, here it is, the K. Oh, God accepted my prayer. I was praying that I will see the K very soon, so at least you will remember. Do you remember that we said that Poisson's ratio is between 1/3 and 1/6? For most structural materials like steel and wood and concrete and aluminum and name it. There is something is called bulk modulus or volume modulus of elasticity. It's famous by bulk modulus without mentioning the whole name, but this is the whole name. And there is no need to derive this equation. We derive this normally in mechanics of materials. So G is equal E divided by 3 times 1 minus 2 nu. If nu is equal 0.5, and that's why mu will never hit 0.5. What is happening here? So 2 times 0.5 is 1. So 1 minus 1 is equal 0. That means that the K is equal E divided by 0. What does it mean? The bulk modulus is equal E, which is the modulus of elasticity, divided by 0. This is undetermined. It's not infinity. Sometimes we'll call it infinity or undetermined quantity. So it cannot really achieve that because there is no such thing exist. There is no such material. All materials, they have a K, as we are going to see later on. Okay, so I needed to be aware of that. This is the bulk modulus, which is bulk modulus. Okay, which of the following is true? The shear modulus is the same as the modulus of elasticity. Bulk modulus is always larger quantity compared to the modulus of elasticity. Bulk modulus can be determined from the uniaxial tension, or volume modulus of elasticity is a function of the modulus of elasticity and Poisson's ratio. Yes, from this equation, K is equal E divided by 3 times 1 minus 2 nu. This is what I need you to know. So if you take, for example, Poisson's ratio for steel, by the way, as all of you know, steel is 0.3, the one listed in the book. So if you say that K is equal what? This E, steel, which is 29 million PSI. Do you remember this number? As I always joke with you guys, or 200 gigapascal GPA. Any civil engineer, even while he is dying, he should remember these two numbers. Okay? So, divided by 3 times 1 minus 2, and I will use 0.3 for steel. So, just to give you a taste of how much is the percentage of K compare, okay, so it is so 0.6, so it is 0.4 here, so 3 enter 0.4 times, and inverse, so this will give you about 0.833 E. For steel, for example, this steel, okay? I'm using Poisson's ratio of 0.3 for steel as, so read all the given information, read all for the possible answers, and select. We are selecting the best, by the way. Sometimes best answers, sometimes answers are so close to each other that you get confused, but we need to get the best. What is the best answer? And let us take a few minutes of break. Right now it's almost 6 o'clock. I need to get some, to continue our discussion. Some stuff I mentioned, for example, delta is equal PL over AE. I mentioned that. Okay, so let me just grab a question from one of you. Sorry to keep you waiting. Sometimes I keep you waiting until I finish something in my head or I'm planning to talk about. Okay, no problem, Larry. Larry from Las Vegas wants to talk to me. No problem, no problem. Keep going, keep going. I will do all my best to help you, okay? Yeah, you can give me a call. There is a class tomorrow, by the way. I am helping a group of engineers tomorrow. They have the exam, serving exam between 12 and 3 tomorrow. You can attend this class. Larry. But you are very welcome to. But reminding, and I did not reserve it yet. I discovered a few minutes ago that I am looking to my note, and I found that I have one item that I need to add. So after this class, immediately I will add the class for the surveying class between 12 and 3. Okay, but you are very welcome to call me. But probably I will leave immediately because I'm fasting, and probably I will leave immediately to break my fast and come. So you are very welcome. Okay, good. Thank you. So yeah, from 12 to 3 tomorrow. That's correct. That's correct. And after that, I believe there's another session tomorrow for the FE. Oh my God. And even I have a Fresno State student from 3 to 4:30. So tomorrow is a busy day for me. So pray for me to stay healthy. Okay. Let's take a few minutes to break and stretch your back and get some fresh air. Air without corona, please. Corona is still around. Okay. Don't say that we are safe now. We are not safe yet. Okay. There is a lot of, you heard the news this morning, or I heard the news this morning. Unfortunately, other countries like India and Brazil and many countries, but those are the two countries they mentioned this morning in the news. 3,000, 4,000 deaths per day, and 400,000, 500,000. And as you know, the virus is mutated. So the virus is moving around. So there's is a mutated, is a change. So I hope that they can find a vaccine that it can challenge all these mutated, so different versions of coronavirus. So still, the situation is still dangerous. Don't say that I am safe now. Take it easy and wearing the mask. I know the CDC, they announced it 2 days ago, that the CDC say announcement that if you are fully vaccinated, you can take the mask unless you are in a crowded space, and I don't know what's the definition of a crowded space. Okay, so if all parties are vaccinated, fully vaccinated, and effective, because the vaccine, as you know, all of you know, that it will not be effective until 2 weeks after the last shot, if you are taking the 2 shots. Okay, anyhow, I'm not a doctor, I'm not a medical doctor, sorry. Okay, so let us come back after 10 minutes from now. Thank you very much. Okay, welcome back, everybody. Brian, I just emailed you the two chapters, the mechanics of materials and materials section. So let's continue our discussion. And this section here is talking about the uniaxial loading and deformation. And again, this is a section that is taken from the FE, the NCAAS FE reference handbook. Sigma is B over A, we know that. Epsilon is delta L over L, or just delta over L, where delta is the elastic longitudinal deformation. And modulus of elasticity E is given, this is Hooke's law, and delta is equal PL over EE. This equation is very, very important, where the deformation is equal PL over AE. This is assuming that we do have a shaft like this, and you are going to see a lot of examples, I believe, if this is P, and if this is L. So after we apply the load, this is going to change to delta L, which is delta in this case. We're using delta L. So delta L is given by the equation B over A, or PL over EA, or BA over, and the equation is very obvious here. This is what I was talking about, the definitions, or the difference between the true and the engineering. The true engineering is talking about the actual or the instantaneous cross-sectional area. This is dealing with the original. Okay, so I need you to know the definition, just in case if they ask you the difference between these two types of definition. The engineering, this is the one we are using, by the way. I'm going to show you a couple of diagrams to illustrate this to you. Okay, the other difference also I need you to be aware of, the difference between the engineering strain and the true strain. Also, they are dealing with the originals. So the engineering definitions, they are dealing with the originals. These are dealing with the instantaneous length. They put the initial length in the NCAAS. I believe this is not very accurate. I prefer to put the delta L over L, which is the instantaneous length, because the initial length, this is the equation given in the NCAAS. I don't agree with that. It should be, this should be instantaneous as this one here, but I will keep it as is. As given. Okay, there is a relationship between, by the way, the epsilon sub t, t for 2, is equal ln is the log to base E, as all of you know, ln, okay, 1 plus epsilon, where epsilon is the engineering strain. Okay, so units, inch per inch or millimeter per millimeter. This is, we usually use it in design. Okay, this we don't use it in design, by the way. I mentioned it here. We are using the engineering definitions. If you flip the page, you will find that here is Hooke's law. Do you remember Hooke's law? Here it is. Sigma, this is within the linear portion. Modulus of elasticity units, PSI or gigapascal. GPA, do you remember GPA, gigapascal? And at the beginning of the NCAAS, by the way, and all of you are aware of that, they have all these abbreviations. So the abbreviations for the, I believe they mentioned at the beginning of the vocalities. Yeah. So what is giga? Giga, okay, which is the 10 to the 6. No, 10 to the 9, sorry. Mega is the 10 to the 6, sorry. Okay, mega and giga, okay, 10 to the 9. Here it is. Kilo is 10 to 3, obviously. So any of these metric prefixes, okay, I need you to be aware of. This is on page 1 of the book of the NCAAS, the handbook. Also, this is a conversion from Fahrenheit to Celsius and so on. 1 gallon of water, by the way, is very important. 8.34 pounds, okay. This is 1 cubic foot of water, 62.4. These two numbers, this is gamma water, and this is the how many pounds in 1 gallon of water, which is 8.34. We're going to use this, by the way, when we're talking about the water cement ratio for concrete mix, W over C, water cement ratio. In fact, they have a problem in the NCAAS, and when I cover the materials tomorrow, I will cover the materials tomorrow, hopefully that. They have a problem here, is a little bit the wording. I wish that it could be written a little bit much better. At least it will not cause confusion. I don't know if they still have it or not. It's a concrete mix design problem. Maybe they are no longer have it here. I will see what. No, here it is. No, they still have it. Okay, problem number 40. the following water is given, and cement and coarse aggregate, fine aggregate. It's the wording, and when I come to the SSD, by the way, stands for saturated and surface dry condition. This is problem number 40 of the NCAAS SSD. So we are going to get the amount of water used. So we need to see how many pounds of water per cubic yard or water cement ratio. We'll talk about all these things, but the wording is a little bit not clear. Okay, I wish that it is written in a different way, and I will tell you what I think. So at the beginning of the book you'll find all these things. Sorry, just try to remember as much as I can. This is the delta is equal PL over AE. Okay, and this is from where it came. Okay, Hooke's law and all these things. And here it is. Do you remember elastic and plastic? Here we go. Strain hardening, and after that at the end necking, and it will fail. So this is the elastic stage. Okay, elastic stage is up to the proportional limit or the elastic limit. We have upper yield point, lower yield point, all these things I talked about, and this is the plastic strain hardening. This is a material that has a well-defined yield point. This yield point here is like this. Go up like this and go down. So this is the upper yield point, and this is a lower yield point. In design, in the steel manual, and I'm sure that all of you maybe or took the steel class, the F sub Y that is listed in the steel manual, okay, like this one here, which you'll see a page, by the way, I took it from the steel manual. Okay, the steel manual, whatever edition you use, all of them, they have the same tabulated values. Okay, they are using the lower yield point. They are using the lower. This is the lower yield point. This is the upper yield point. Yield point. The reason for that, they said that this upper yield point is temporarily and for a short duration. So it is a transition between the elastic stage and the plastic stage. So they don't rely on design. They rely on the lower yield point, which is this one here. So the F sub Y listed in the steel manual is the lower. And this is something we call it F sub U. You are going to see it in the table, which is the ultimate. Okay. So I need you to be aware of this. This is, for example, another stress strain curve. This is for a material does not have a well-defined yield point. Okay, as you can see here, it is curved. So how we define the F sub Y? The F sub Y, they are using what is known as 0.2% offset. Okay, the slope obviously is the most of elasticity. They are using what is the offset method, which is 0.2%. This is, we talked about this at the beginning, which is a strain of 0.002 inch per inch. So this is strain. Okay, and this is F sub U, which is a tensile strength, which is the ultimate here. Another stress strain curve. Okay, they ignore, this is a design, by the way. This is the one we use it for design. So we ignore this hump here. So they decided to ignore it, and the F sub U and the F sub Y, those are the tabulated values. You'll find them in the steel manual. For example, A36 steel, for example, 36 KSI or 36,000, and the F sub U, which is the tensile strength. Well, we need these two numbers, by the way, when we come to the steel section. Okay, the steel design, okay, which is one section of this civil engineering. This is concrete. And you will find series of equations. Okay, this is the structural design, and the steel is coming in the following section. This is concrete. Here we go. Okay, so the steel, you will find that on page, for example, on page on page 282, page 282 of the NCAAS book, you will find here it is. This is F sub Y. Okay, and this is F sub U. So this is F sub U and F sub Y. One design for one design parameter is based on the yielding, and one is based on the rupture or failure. So one we need to get F sub Y, and one we need to get F sub U. The one you are going to see it shortly. Okay, so we are using the F sub Y and the F sub Y. But F sub Y, the one listed in the steel manual, this is a lower yield point, lower yield point. They ignore the upper yield point, as I told you, because it's a transition for short duration, which is this hump here. Okay. If you flip the page, you will find, this is, by the way, this is from the steel manual. Here it is. The ASTM, the American Society for Testing. So, for example, this A36 scale, this is the F sub Y, and this is F sub U. These are the tabulated values, the ASTM specification for various structural shapes, the W shapes, M shapes, S shapes. We are going to talk about these things in the steel section. So if you flip the page here, you will find that the problem 610. Okay, 610. I gave you the following scenario. Aluminum rod is shown, fixed and free from the other end, subjected to all these forces, F1, F2, F3. The diameters are given, okay, and is asking the maximum engineering stress. Stress is equal P over A, and the engineering we are using the A sub O, the original cross-sectional area. So sigma is equal P over A. Okay, since we are talking about the engineering, so we are using the original cross-sectional area, and is asking for the maximum. Okay, so if you look to these forces here, I have F1, F2, F3. Let me get closer here, at least you can see. If you don't have the book with you today, no problem. Okay, this is a problem 610. Okay, and the length is given. Okay, the diameters are given. And the area is equal by D square over 4, as all of you know. Don't forget this, which is given here. But I need the force. So section AB of this shaft is subjected to a maximum force. This is 12 kibs. A kib, by the way, is 1,000. 1 kib is equal 1,000 pound. And it's to the, if you put in the X, Y, in the positive X. F2 is in the negative X or opposite. And F3, F2 is given to be what? Is 16. And F3 is 28. All of them are in kibs. So when you come to this section here, section AB, if you cut, how much force is acting here? I have 12 plus 28. This is 40. But 40 and 16 in the opposite direction. So the difference between 40 and 16 is what? 24. And in fact, this reaction here, by the way, is 24. Because 24, because again, equilibrium, sigma force X equals 0. I have 16 plus, 16, 12, and 28. So I have 16 and 24 is 40, and 12 and 28 is 40. Bingo. So it is satisfied. So the equilibrium equation. So this section has 24 kibs. This section here, which is from BC, it has only 12. Okay. And if you cut it and you consider right or left, you'll get the same answer, by the way, when you cut the cross section. So this section BC is subject to 12. Okay. Because I have 24 here and 12 will give you. Okay. Or if you look to the 16 and 28 is also is 12. And finally, this section, which is CD, CD is subjected to this force here, which is 28. So I calculate the stress based on the force acting on the member, and we got this number and this number and this number. Obviously, the largest number is this one here, which is the 396 KSI, kibs per square inch. Very, very interesting problem, and we need to be aware how to calculate the force. That look at it and always draw a free body diagram. Free body diagram. If you look to problem number 11, 611, shaft, and is asking the vertical displacement at C with respect to A. This point here, C, and this is a force F or P. He told you that the P is equal what? The load applies equal 5 kibs. Okay. So as this force is applying tension on the member AB, it will move down. This point also, it will move down at the same rate, because there is no force, there is no deformation here, by the way. If you look to sigma of the member BC, what is the stress in the segment BC? What stress is 0? There is no stress on the segment BC, but there is a stress here. Segment AB is equal the force, which is 5 kips P over A, 5 kips over the area, which is by D square over 4. If you look to the deformation of this member, what is epsilon or delta, the deformation delta of the member BC, this deformation here is going to be 0 also, because there is no stress, no deformation. But delta AB exists, which is this one here. I needed to be aware of that. So this is delta is equal PL over AE 24. 5 kips 24, 2.5, 29 million, 29,000 in this case. I used 29,000. Do you remember the mass of elasticity? Okay, so 0.0016, which is the answer. Okay, C in this case, the closest answer. Okay, so these things, okay, this is the table I'm referring to. If you flip the page, you will find that another section of the NCEES, here it is. It's called thermal deformations. Delta T, the deformation due to the change in temperature, is given as alpha. Alpha is called coefficient of thermal expansion, alpha. How can I get alpha, by the way? From where you get alpha? Do you remember the two tables in the NCEES, table 1 and table 2, at the end of the mechanics of materials? Here we go. This is the table I was talking about before on page 138. This is a coefficient of thermal expansion, alpha. You don't have to memorize anything, but they are given here in US and in metric, or the SI. So again, we need to know where the information, because this book will not be available to you in your hands on the exam. You are not going to go to the exam, just calculators only, and that's it. And I don't know, they provide you with the paper, and they provide you with everything. Read the NCEES, okay, exam requirements, and what you're supposed to carry and what you are not supposed to carry. I believe they have lockers outside, okay, the testing site, where outside the room, obviously the computer room, where you can lock your personal stuff like cell phones or keys, and they don't allow you to go. And when you go to the restroom, they search you, and you come back from the restroom, they search you again. It is not an easy, okay, so we need to be ready. So we need to know exactly where. So this is a coefficient. This is in table 1 on page 138. Okay, so here it is, table 1, typical properties. Probably I put page, probably next time I'll put page 138. I put the table, no, but I didn't put the table of the NCEES, obviously is not any other book, NCEES. So L is the length, and T sub O. T is the final temperature, and T sub O is the initial temperature. And amazingly, by the way, you are going to see this equation later on after you finish your FE and you go to the PE in California, BE in California. They need a surveying exam and seismic exam. Surveying exam, the one my friend was asking me about, in my surveying book, 4 books for surveying for California, and you'll find in chapter 4, you will be amazed that this equation is there. Here it is. Alpha T minus T sub O times L, where alpha is the coefficient of thermal expansion. So this is the change in the length. Okay? So the equation is going to be mentioned again in a different class. So here is the equation, okay, and very easy to derive all these equations and how to get. So this is I need you to know this delta t, which is a change, okay, or the deformation that will be caused. I added some additional equations just for your knowledge, but you are not obligated to know that. For example, the combined loads, okay, with thermal deformation. For example, epsilon is sigma over E plus this one here, which is alpha T minus T sub O. And the change in length is given by this. This is if you have the combination. Sometimes they give you combined problems. One due to load and one due to temperature, which is alpha L T minus T sub O. So the equation that I number them here, they are not given in the NCAAS, but sometimes they ask, by the way, I heard some questions that you should be able to figure it out. Okay, and this is what I am trying to prepare you for that. The problem number 12. An aluminum bar at 80 Fahrenheit is inserted between two rigid stationary walls, okay, by inducing a compressive stress of 10,000 psi. I have a shaft, aluminum, and I hold it between two fixed ends. And I insert this bar between these two such that the existing compressive stress, sigma compressive, sigma C, by the way, we're using C for the compressive, is, this is 80 Fahrenheit. Okay, so right now this is at 80 Fahrenheit. What will be the temperature that the bar will drop out, where the strain will be 0? Okay, so if the member will shrink because the metals, as the temperature goes up, they will expand. Okay, and as the temperature goes down, so they will shrink. This is what we do for steel tapes in surveying. We need to adjust the length of the tape. So if the temperature, the standard temperature for steel tapes is 68 Fahrenheit. 68 Fahrenheit, this is standard for calibration of the steel tapes. So if the temperature is higher or lower, we have to adjust the steel tape because the steel or the tapes will elongate and also will shrink. So this is the equation here. Epsilon sub T is alpha T minus T sub O. Okay, alpha is a coefficient of thermal expansion. Okay, and here it is. From where I get this one here? From the same table, table 1 of the NCAAS. I pick a number 13.1 times 10 to negative 6. Let me see if I pick the right number or not. Okay, this is aluminum. He didn't see what type of aluminum. Aluminum, here it is. Here it is, this number here. 13.1 times 10 to negative 6. It says here negative 6. So be careful with units. Units is a source of errors or mistakes. Okay. So I plug it into the equation and I ended with a temperature of negative 1. So we need to lower the temperature from 80 Fahrenheit to negative 1.88 in order to this bar will drop, because as we lower the temperature, it will shrink. Okay, it will shorten in the length until it will be stress-free when they drop out of this. Okay, so it's very good. Okay, so another problem, a steel bridge has a span length of 1,000 feet. The difference in length in inches between January and August. January we have negative, and August we have 100. What is the change in length? So we have a bridge, okay, steel bridge, and the length is 1,000 feet. And in design, we consider that. We have expansion joints. Okay, so the steel bridges, when they expand during the winter, during the summer, sorry, okay, they must have, okay, enough room to expand without causing the stress, okay, without increasing the stress on the bridge. And you will know this in the bridge design later on. So here is the equation. And they plug it in. And alpha, steel, 6.5. Again, from the same table. Here it is, 6.5. Okay, table 1 on page 138. So this is, you flip the page, we are talking about another section of the NCEES. Cylindrical pressure vessel. When we have a pressure vessel, basically a tank, it could be a circular, or it could be the tank that you have propane gas tank that you see it, okay, by propane gas. So when we fill these with gas, it has a pressure inside. So when we design these pressure vessels, we need to know the thickness. What is the proper thickness? Otherwise, it will explode because the pressure inside. So we have atmospheric pressure outside, and we have a pressure built in due to filling this with propane gas, whatever. So they came up with these equations in order to help us to. So one of you is raising the hand or have a question. Okay, you are very welcome. Okay, thank you. Okay. Sigma T and sigma R. So there are two sigmas. Sorry, the text is a little bit faded. Sigma T and sigma R. Sigma T, we call it tangential or the Hooke stress. And sigma R is the radial stress. So if you do have a cylindrical shaft or a cylindrical tank, subjected to a pressure inside, there are two stresses will occur, like this tank here. So one is tangential, which is tangent to the circumference, is called sigma T. And the other sigma, it's in the radial direction, which is sigma R. So these definitions are given as, I believe I have some drawing here. Yeah, just basically the pressure and so the tangential stress is given by this equation, where the Ri is the inside radius and Ro is the outside radius. So this is the stresses at the inside walls are given by this equation. For external pressure only, the stresses at the outside walls, okay, is given by these equations. And the P sub I internal pressure, this is a P sub I, and P sub O is external pressure, P sub O. And they adding another equation here for vessels with end caps, the axial stress, where we have caps at the end here, is given by sigma axial is equal to the internal pressure P sub I, R sub I, R square minus. All these equations are given here. The thickness T, by the way, the thickness T, the wall thickness T is the wall thickness. If the thickness is small, when the thickness of the cylinder wall is about 1/10 or less the inside radius, when T less than or equal 1/10 of the inside radius or inside, they call it thin-walled pressure vessels. Thin-walled. So what is a thin-walled? Thin-walled. If the T is less than or equal 1/10, less than or will be thickness is about 1/10 or less. Yeah, so less than or equal, that's correct. Of the inside radius, they classify this kind of vessels thin wall. These are thick, by the way. These are thick. Walled vessels. This is thin walled vessels. So the previous equations will be reduced to these two equations. Sigma tangential, and T is the thickness. Here it is. The T is the thickness. And sigma axial. One tangent to the circumference of the, it's called sigma tangential, and sigma radial or sigma axial. So the axial is equal pi r over 2t, and this is only divided by t. So I need you to know that sigma tangential is 2 times sigma axial. The tangential stress is divided by t only, divided by 2t. Or sigma axial is equal 1/2 of sigma t, whatever you would like to call it. I need you to know that. And this is only, it is for what? For thin-walled vessels. This R here and this R here, that's going to be used. Which R is going to be used? They came up with what is known as the average radius. So if this is the pressure vessel, here it is, and this is the thickness T. So we do have two radii. Radii is the plural form of radius. Radius, it is two radii, R-A-D-I-I. This is the plural form of radius, as all of you know. So this is R-in, and this is R-out. Outside radius and the inside radius. So the equation for the thin-walled vessels, we have two, and I need you to be familiar with this. Sigma tangential, which is P R divided by T. And the axial, sigma axial, we said half, so it is PR divided by 2T, where the P is the pressure, by the way. The P is the inside pressure, or the internal pressure. Let me put P sub I. So the internal pressure. Is this correct? Yeah, P sub I. If I write an equation wrong, please correct me because I'm using my book, but we need to be aware of these equations. They are here. Sometimes I need to go back and make sure that here it is. Here are the equations. This is on page 132. Page 132. This is sigma T and sigma okay, and T is thickness. This R is defined as the average of the Ri plus Ro divided by 2. Is this correct? Yeah, 2. They are using 2, which is the average radius, because we have inside radius and outside radius. They decided to go with the R, which is average radius. This is what's given in the NCEES. I took this and spelled it into English, as you can see here. So cylindrical pressure vessels, they could be thick, where the T is greater than R divided by 10. If it is a thin, thick, I'm still talking about thick. Wait a second, this is thick. So here are the equations. I wrote the equations again. Okay, obviously it's much cleaner. Okay, here it is. These equations, it's basically these equations here. And for external only is given here. So and all these parameters are given. Okay, for vessels with end caps, the axial stress is given by this equation, which is given also in the NCEES. Here it is. For the end caps, here it is. It is a P sub I, Ri, R. They should match the equations given in the code or in the NCEES. Sorry, I said the code NCEES, which is a reference. But for the thin walled pressure vessels where T is less than, so they came up with these two here. One is tangential and one is the axial, and the average radius is. So the tangential stress, by the way, they call it Hooke stress. And it is twice the axial, as you can see here, that sigma tangential is equal to sigma A. Or sigma A, the axial, is equal sigma T divided by 2. I need you to know that, because sometimes they call it Hooke stress. Hooke, okay, Hooke stress. Okay, you know the wheels, okay, they manufacture way back for the carts, okay, they have, okay, this, and they put some metal here around it, is a Hooke stress, okay. Okay. If you flip the page, you will find problem 614. Say that a cylindrical pressure vessel with a wall thickness of 1 inch and the internal pressure 200 psi, and an outside diameter is given to be 4 inch. The tangential stress. Here he did not tell me it is a thick versus thin. The wall thickness T is given to be 1 inch. So outside diameter, so this is, here it is. Sorry, I'm drawing my cylindrical like eggs, but believe me, they are very close. Here it is. So this is the inside diameter, and this is the outside diameter, D out. And obviously the thickness is the difference between them divided by 2. Okay? Because two thickness, T here and T here. So in this case, the radius is equal what? If we give you the diameter to be 4 feet, 4 feet is 48 inches. So the outer radius is 24 inches. So the inside radius, okay, 24 minus 1, and the T is 1 inch. Be careful with dealing with radius or diameter. And you know the diameter is equal to R. So I check this criteria. Is T less than Ri over 10 or not? So it is 1 inch is given, and the inside radius is 23 inches. I am suspecting something here. let me double check something. I did a mistake probably here in the problem. It could be a typo. So this is 1 inch and this is 1 inch. And he said that the outside diameter is 4. So this is equal 4 times 12 is equal 48 inches. So the inside diameter is 46 inches. Oh, that's correct, 23. So, which is divided by 2 will give you 23. So no, it's correct. It's not a typo. I thought that I missed something here. Okay. So this is the inside diameter, and the inside radius, obviously it is 46 divided by 2, okay, which will give you the 23 inches. Okay. So I use the radius, I subtract only 1 t, because the diameter you subtract 2 t's, one from here and one from here, as all of you know. So after this test, I said yes. What yes means? That 1 inch is less than the inside radius, which is 23 inches divided by 10. So it turned out to be, therefore the vessel is considered a thin. And he is asking for the tangential. Tangential is given by this equation. And R is the average. Here it is 23, 20 divided by 2. Bingo. This is a very common problem, by the way, you might see on the exam. It's 4,700, so the answer is A. And also check sometimes, by the way, I rearrange these answers. So make sure that this one here, normally I check this, and this, and this, they should match. Okay, so the final calculation, okay, it should match the answer that has been selected, A, because sometimes I rearrange these. Another section. Stress and strain. This is what's given in the NCEES. They came up with these two equations, which is sigma A and sigma B. Sigma A and sigma B, they are known as the principal stresses, by the way. Principal stresses, where sigma A comma sigma B is equal sigma X plus sigma Y divided by 2, a plus or minus the square root of sigma X minus sigma Y divided by 2 square plus tau XY. Tau XY is the shear stress. Okay, and sigma C, which is, this is the two-dimensional. So the third one must be 0. Okay, which is 2D stress. We can draw the state of stress on an element like this. So this is X and this is Y. They call this is sigma X and this is sigma Y, because this is in the X direction and this is in the Y direction. And we have what is known as the shear stress. This is called shear stress, which is a tau XY. Tau XY and tau YX, they are equal, by the way. They find this and this must be equal and opposite for equilibrium. Obviously, we are showing the other stresses. So this is the general state of stress in 2D. It's called the plane stress. Okay? We can use Moore circle. Moore, Professor Moore is a German scientist. He used these equations, okay, the equations for the stresses, in order to get what is known the principal. Here it is, the word the principal is very important. The principal stresses. The principal stresses. Sigma A and sigma B. We can use Moore circle, and we're going to see Moore circle shortly. Through some equations, nobody will ask you, we can derive the equations. When you have a plane that has inclination theta, we can do all these fancy equations and expansion and all these things. And we can end it with this equation here. And he took these equations, Professor Moore, and generate Moore circle. I will show you the Moore circle in just a second. But not necessarily on the exam, you are going to use Moore circle. Not necessarily, okay? Moore circle is coming. But, for example, this problem here, I remember I saw a problem this morning. If you remember the NCEES, Here it is. Problem number 33. Because I don't like you to jump immediately and draw more circle if there is no need for it. So the maximum in plane shear stress in the element shown. So if this is X and this is Y, normally they assign axes, but if they did not assign axes, in this case, so this is sigma X and this is sigma Y. And this is a tau XY or tau YX, whatever is convenient for you. Both of them are equal, by the way. We call this is a tau, okay, X, because this is a face in the X, XY, and the other one we call it tau YX, but they are equal mathematically. And he's asking for the maximum. And maximum what? Maximum shear stress. If you look to the Moore circle, first I will explain it. And this tau XY, and this is sigma X, comma sigma Y. We are using the x-axis to represent the normal stresses. These are normal. Sigma X and sigma Y, we call them normal stresses, normal stresses. This is called shear stress. So for example, if I would like to plot this, I know more circle is coming, but let's introduce it here since we have a problem in front of us. Interesting problem, and it will help us to understand what's more circle and what are the. So normally we draw this into scale, by the way, but not necessarily to do it in a scale here because we can use the mathematical relationships. So sigma X is 40, so I will use 40. This is 40. Assuming this is 10, 15, and so on. And I have tau XY is, this here is counterclockwise. And this is clockwise, as all of you know. Here it is. See? Clockwise, counterclockwise. And I have an engineer, a friend of mine, is told me that, Dr. Mansour, all the thing digital nowadays, how I know clockwise and counterclockwise. I told him, very simple. Go to Walmart, buy a $5 watch, it has, and you can see what's the clockwise and counterclockwise. So at least you remember that. In the Moore circle for sigma, let me put sigma. This is sigma tension, by the way. This is tension. How I know it's pulling, and this is also tension. They agreed, who agreed? Your grandfather and my grandfather agreed that the tension is positive. And some problems they are going to see later on that this is compression or compressive force. So the tension is positive and the compression is negative. So this is agreement between your grandfather and my grandfather. Don't upset them, please, okay? This is for the normal. Tension is positive, compression is negative. As far as the direction of the shear stress, because one is counterclockwise and one is clockwise. Let's look to see what the NCEE has said that if you learn it in school differently, we need to stick with this. Anything you learn in school that is not in agreement with what they are using here as simple as notation, we need to respect that because this is the only thing that you are going to see. Okay? Let me see if they mentioned this or not. If I remember, it was mentioned somewhere. Here we go. This is on page, this is a Moore circle 2D. To construct more circle, the following sign conventions are used in order to make everybody getting the same answer. So they are putting the sign convention that is listed in Mechanics of Materials books with some kind of variation from one book to another, but this is what. So normal tensile stress and compresses are plotted compressive stress is negative. So compression is negative. So components, or not components. So compression is negative and tension is positive, as I just mentioned. This is, by the way, on page 133. And do your best next time. If you don't have the book this time, try to bring the NCEES. The second element, that for constructing more circles only, shear stresses are plotted above the normal stress axis, which is the y-axis. This is the sigma, sigma x, and sigma y. And this is the tau xy and tau yx, or vice versa. And they are saying here tau cw and tau ccw, the counterclockwise. They are saying that shear stresses are plotted below from the counterclockwise couple. So we have clockwise. So this is a positive and this is the negative. But in order for them just to make it very clear, so they say that this is the sigma clockwise and this, not sigma, I'm sorry, tau. See that I got so hungry, so it seems I start to mix them. Just, I will eat after 45 minutes and drink like you guys, okay? I know some of you are fasting also, so bear with me until we break our fast around 7:44 today, or 7:45, I believe. So this is clockwise, which is positive, and this is a counterclockwise, which is negative. This is the equation we just saw, by the way. Let me show you the equation in my book here. But before our professor, this is the equation that this is on page 21 of my chapter. This is mine, okay? The sigma A comma sigma B is equal sigma x plus sigma y divided by 2, and the plus or minus, because we have maximum and minimum. But it is sigma A, that one is called the principal and one is called the major and the minor, or the maximum and the minimum. A plus sigma x minus sigma y squared divided by 2 square, a plus tau xy, and take the square root. You will find that the NCEES, they have the same equations, but here it is sigma x plus sigma y divided by 2. This is going to give me C, which is the center of the circle. And the radius of this circle, which is R is the radius, is equal the tau max, which is given by this equation here, which is the square root of sigma x minus sigma y divided by 2 square, plus the tau xy square. Because this is the maximum shear stress, either positive or negative. It does not make any difference because the radius is the radius. These two stresses here, which is this sigma A and sigma B here, this is where the shear stress is equal 0, because the shear stress is 0 here. So this is a minor principal stress, and this is a major principal stress. So going back to the problem of the NCEES, can we draw more circle? Yes, we can. But he is asking for the maximum shear stress, which is the tau max. The tau max, we said that after we draw, let's look to the other day. So counterclockwise is negative. So this is 40, and this is 10. I will go, let's assume this is negative 10 is here. Let's assume this is, try to make it 10, negative. I will locate one point, which is this face here. This is the 40 and the 10. If you look to the other one, I have 20, and I have a clockwise of also 10, so, but I will go up 10, plus 10. So I will locate one point here. These 2 points, if you connect them, they will intercept with the C. This is the center of the circle. And this, by the way, this is the radius, R. So if you come and you draw a circle, let me draw a circle. Hopefully I can draw a circle, not like an egg, but oops. These 2 points has to go through the circumference of the circle. This is what is known as the Mohr circle. The Mohr circle will intercept with the x-axis. This is the sigma min, and this is sigma max. So the tau xy, I can get it as the radius, because this is also the radius, which is the maximum shear stress, either positive or negative. It does not make any difference. So the tau max is equal what? Is equal the radius. But the radius is given to me as the second term, which is the sigma x minus sigma y divided by 2 plus the tau xy square. So what is sigma x? Sigma x is 40. So I will plug this here is 40 square, by the way. Sorry, I mentioned the square, and the tau xy square also. Okay, so for catch my, so it's 40 minus the 20 divided by 2 square plus the tau xy square. The tau is 10 is square. If you do this simple math, which is 40 minus 20, which is 20 divided by 2 is 10. 10 you square it, it's 10 squared, so 10 squared, so it is 200. 200 and the square root, I get 14.14 KSI. This number here. So if I have 14.1, this is the answer P. Bingo. I hope this is the correct answer. Check the answers to see if this is correct or not. If it's not correct, at least I can correct myself. But we need to understand, sometimes this is a hard way or the time consuming, but we will discuss it. But we need to understand what he is asking for. Sometimes they ask what is sigma max and sigma min, or sigma min and sigma max. Okay, sigma max and sigma min, we are going to see them in just a minute. That which is the maximum sigma max and sigma min. Sigma max is C plus R, and sigma min is C minus R, which it can be translated, by the way, like this. This is sigma x plus sigma y divided by 2 plus the one we just calculated, which is R, which is the radius, is sigma x minus sigma y divided by 2 square plus the tau xy square. This one here with the minus, sigma x plus sigma y divided by 2, there now is minus. A square root of sigma x minus sigma y divided by 2 is square plus the tau xy square. These equations are given and in the NCEES, and we are going to, here it is, you'll find that I'm not inventing anything. I just here it is the radius. So sigma A, which is the max, it is C plus R, and sigma B is equal, or C is equal sigma X plus sigma Y divided by 2. They separated the original equation, which is sigma X plus sigma Y divided by 2 plus or minus the square root of sigma X minus sigma Y divided by 2 square plus the tau XY square. I needed to know that. Okay, so I need to be aware of all these things. Okay, so my God, time is flying. But what can I do? The day is only 24 hours, as I told you, and the Egyptians who came up with this idea. So, here we go. Here, so if I go right now to a sample problem that I have, obviously C is given here. All this you will find it. So basically, it is the repetition of what I just said. Problem 615. I gave you sigma X and sigma Y and tau XY. Sigma X is negative, meaning that this is compression. If you would like me to draw this state of stress, here it is. If this is X and this is Y, so sigma X is negative, mean compression. This is sigma X is equal to 3 KSI. Not necessarily that the problem will be given like this. This is, both of them are tension. And this is why both of them are positive. This is positive and this is positive, as we agreed upon. Okay, so, and the sigma Y is tension. Here it is. So this is 5 KSI. And this is sigma Y. And the same story here. As far as the shear stress, one this way and one this way. They are equal for equilibrium. This is the tau XY, which is equal to 3 KSI. This, it could be given instead of wording like this, it give you like exactly like the problem in the NCEES. Okay, the state of stress, here it is. An element is shown. This is the state of stress for any given element. Here it is. I could remove this completely and give you this drawing. But we need to understand the relationship between this and this. They mean the same thing. And it's asked what is the maximum principal stress? Maximum. Which is, the R is given, here it is, C, and sigma A is the max, and sigma is the min. So the maximum, obviously, is a 6 KSI. And as you can see here, he gave you two answers, 2 6s, okay? 6 KSI and 6 KSI. But the angles are different. So if you have only 1 minute left and you calculate this easily, you can get this very easily 6. So obviously this is out and this is out. Process of elimination. And you did not calculate the angle. And you can see the angle, by the way, this is half of this. Or this is twice of this, because this is a common mistake sometimes we do. Because the orientation of the principal stresses in Mohr circle, we take the angle, by the way, this angle is 2 phi. I'm going back again to the NCEES on page 133, which is the same thing. So 2 phi. Or this angle is called, he called it 2 phi. So this is normally what is given, the 2 points on the circumference. I connect them, they will intercept at the C, and this is the radius, and after that we draw the nice circle. And the angle phi, I believe, is given on the following page. Or they did not give it to you. I don't see it. Because they know we are smart. Okay, so if you look this, take this triangle out. This is the angle 2 phi. I know from here to here, it is the tau xy, which is from here to here. And I need this distance from here to here, okay, which is this distance from here to here. How much this distance, by the way? I gave it to you, by the way, as I give you the angle directly, okay? Okay, that's fine. Or there is another option. Sorry, no. Let us use the other option. This is a point on the circumference of the circle. So this is the center of the circle. So this is what R. So what is tangent? Tangent, instead of using sine, we can use tan. Tangent 2 phi. This tangent, this angle is equal tau xy. No, it will not work. This will give you the this over this will give you the sine. No, I use the tan. So this is, I will call this is x. Okay. So the tan 2 phi is equal to tau xy divided by x. So I took this. So what is this x here? Which is the distance from here to here. Okay. If you look to the problem I gave you, and I will show it to you in just a minute, it is, I use 2 theta is equal tan 3 over 5. 3 is the shear stress. So the triangle is like this. The triangle from the Mohr circle is like this, which could be any triangle, by the way, not for this specific case. Okay. This is for a given problem here. So this, or let's take the upper triangle, like for the sample problem here. So this is a y and this is x. So right now, this here is a 3, which is the tau xy, which is given to be 3 ksi. And this distance from here to here, which I call it x, and this is the angle 2 phi. So tan 2 phi is equal to 3 over x. Okay. This here, by the way, this is a given sigma. This is sigma y. And from here to here is sigma x. Okay. And this is the center here. So this distance x here is basically is equal the radius minus sigma y. The radius minus sigma y. It should be. And the radius is 5. And the sigma y is 5. No, it cannot be. There is something, okay. I'm missing something here. Okay. Let me see. This distance x here, I know this is sigma x. Oh, sigma x, and this is sigma y. Okay, I got it. Okay. This distance x here is sigma x minus sigma y divided by 2. Okay, so in this case, and we take the absolute value, the sigma x is minus 3 minus 5 divided by 2. So this is 8, and still not getting right. I am doing something wrong, because this is sigma x. Three or sigma max. Sigma max is, I get it to be 6. 6 minus 1 is a 5, yes. Yeah, but sigma max minus c, but this should work. I think there is something wrong here. Anyhow, I will be glad to correct that. So the angle theta in Mohr circle, let me just, it seems to me that I don't like to spend too much time here. I thought that they give you the angle directly. Let me see if the angle is given here. Okay, no. Okay. Okay. So, no, it's not given. I don't know why they didn't give you the angle theta, but that's fine. Okay, I will look at it and try to just to. I'm missing something here. This over this, so the x, and this is sigma x, and this is the center. Okay, this is c. So the x is equal to sigma x minus c minus c. Okay, and c is equal sigma x, let me derive it, minus sigma x minus sigma y divided by 2. That means that it is sigma x minus sigma y divided by 2, which is, I said before, sigma x minus sigma y divided by 2. So sigma x minus sigma y divided by 2. Why doesn't, I believe there is a typo here. It must be, there must be something here. I will look at it, okay? I don't like to hold you more than that. So the angle theta can be determined, which is the orientation. So the magnitude is very easy to get the maximum shear stress or the maximum principal stress. In this case, it is C plus R, which is the other end here. So I will look to this to see if there is something either, it does not make sense to me here. Okay, let's keep going, so of course we still have about a few minutes until I quit, so I can go and eat. It seems that I got so hungry. Okay, Mohr circle. So this Mohr circle, these are the two items that I discussed. Oh my God. Okay, and this is basically what is given. This is the C. Okay, the distance C, which is sigma x plus sigma y divided by 2, where this is sigma x and this is sigma y. Okay, and so the distance from here to here is the C, by the way, sigma x plus sigma y divided by 2, and the radius, which the one we use it, is sigma x minus sigma y divided by 2 square, tau xy, and the sigma a, this is the maximum, this is the maximum, and this is the minimum here, minimum, sigma min. Okay, so I need you to be aware of that. He gave us a lot of equations here, by the way. This is for 2D and 3D. The two-dimensional equations, this 3D, a plane stress where sigma z is equal 0. This is epsilon x, epsilon y, epsilon z. And this is the shear stress, you remember, by the way, gamma, which is a shear modulus. And okay, and it can be put in a form of a matrix like this. Okay, for the uniaxial, which is 1, okay, a plane stress means this is 2D, this is 3D, and this is 2D, and this is 1D, which is the uniaxial where sigma y and sigma z are equal 0. So it's called uniaxial stress, which is sigma is equal b over a, okay, which is, we can express it this way also, as sigma x is equal E times epsilon sub x, and sigma is equal E times epsilon, because this is Hooke's law. E is equal sigma over epsilon, or sigma is equal E epsilon, as all of us know. Okay, so this is something that this is also the temperature change from T sub I to T sub F. So there will be a thermal stress, and the equation for epsilon sub x is given by this way, which is combined, by the way. Okay, so this is, again, alpha is a coefficient of thermal expansion, which is this one here. I wrote the equations again, provided here. And these are the equations also given. Problem 6.16 is giving you a steel plate in a state of plane stress, which is 2D, okay, having epsilon sub x, epsilon sub y, and gamma xy are given. If the Mansour elasticity is given and Poisson's ratio is given, the stress components, okay, the epsilon sub z, okay, the stress components and the epsilon sub z are, okay, are given by one of these values here. So again, it's a lengthy equation. Okay, these are the equations that's given. Okay, and I substitute for the values. And finally, I got the epsilon sub z as given to be this amount here. So again, it's not straightforward problem, but I need you to be aware of it. This is the state of stress in 3D. Okay, x and y and z, and this is the right-hand rule. If you move from x to y, you are going to advance in the z. It's called right-hand rule. Okay, and I'm showing you all the stresses, okay, of this 3D, okay, to show it to you. Torsion is important. Tau is equal TR divided by J. Tau is equal TR divided by J. This is the torsion stress circular solid shaft, okay, for a solid or a thick walled. Thick walled, by the way, the thickness T, it must be greater than 1/10 of the radius of the shaft. J is known as the polar moment of inertia. And the polar moment of inertia, by the way, are given in this, in the statics section, which is Ix plus Iy. If you go to the NCEES, page 111, page 111. So, no, they are not here. Radius of gyration, polar moment of inertia. No, which is Ix plus Iy. Probably this is the reason why they didn't put, unless maybe they give it in the, no, in the mechanics of materials, no, it's not. No. So the polar moment of inertia, this is the, unless it is mentioned, I remember I saw it. Oh, this is the radius of gyration R. This is a product. This is a moment of, this is a area moment of inertia. No, probably it's not in this book for some reason. For some reason, I don't see it. No, they have it here, by the way. They have it. They have it for circular shafts. Yes, I saw it here. If you go for circular shafts, this is the J. So this is on page 112, because I remember I saw it here. So J is the polar moment of inertia. J is equal Ix plus Iy, by the way. The sum of the Ix plus Iy. And they give it also for the hollow shaft. So I need you to know these two, because torsion problems normally, it will be either for a solid shaft, solid, this is a solid shaft, and this is a hollow shaft, where they are using A and B, by the way, instead of R in and R out, or the radius, inside radius and outside radius. So if you look to this, you will find that the Ixc is equal pi a to the 4 divided by 4, and Iy also the same. So if you add them together, so it is pi a to the 4th divided by 4 plus pi a to the 4th divided by 4 will give you exactly the pi is a to the 4 divided by 2, since it is Ix and Iy are equal for this case because circular shafts. And this is why we later on we are going to talk about columns. Columns, by the way, we prefer to have columns, circular columns, because of the radius of gyration. The radius of gyration will be the same for the Rx and the Ry. They are the same. Here it is, Rx and Ry are essentially the same. And we are going to see why we prefer circular columns instead of using rectangular columns. And anyhow, so the polar moment of inertia is given in the statics section. And you need to know where these things, by the way, because you have no time during the exam to spend time searching for stuff that we need to. Okay, so this is a very important equation. Tau is equal TR divided by J. They give us the definition of the torsion strain, which is gamma, okay, which is a shear strain, and they define all these things. We have something is called phi, which is the angle of twist, and the angle of twist normally expressed in radians, and this is equal TL divided by JG. So theta, or he's using phi. Phi is equal TL divided by G by GJ or JG, whatever the order. The angle of twist, because if you look to the shaft, if you look to the shaft, a circular shaft subjected to torsion, so this is the center, and if we draw a horizontal line like this at the beginning before we apply the torque, and after we apply the torque, you will find that this line AB, this becomes B prime here. So, and this is gamma, by the way. This is the angle phi. It's called the angle of twist. The angle of twist, that before we apply the torque T, so the angle phi is the angle of twist, and the angle phi is given by this equation. It is TL divided by GJ. So two equations, and normally we express this in radians, by the way, radians, okay, which is pi over 180, as you know. So and the shear stress tau is equal TR divided by J. TR divided by J. Okay. So so the angle of twist is theta, and remember T is the torque and L is the length of the shaft. Okay. And for the thin-walled shafts, because this is for thick. This is for thick, like the pressure vessels we have thin and thick. Here we have thin. They came up with this equation. Tau is equal T divided by 2 A sub M times T, and the parameters are given here. So those are the equations for the torsion I needed to be aware of. I do have a little bit of discussion here. Again, just to elaborate more, you are very welcome to read this. Just is giving you an idea about, this is also from Mechanics of Materials books. But we need to know how to apply these equations. So problem number 617. This section is very healthy, by the way. I have tons of problems, or many problems instead of tons, as my lawyer always advised me, don't use the word tons, use many. Okay, sure. And at the end of this, by the way, columns, we're going to talk about columns. Oh, okay, still have a lot of things. You will find additional problems at the end, Brake's problems. Okay, I don't know how many did I include, but I believe I include a bunch of them. I include about 28 problems. So in addition to the problems in this section, which is about 34 problems, sample problem 34. So 34 problems plus the 18 problems, I said 18 problems, no, 28. Oh, 28, yeah, 28. So this is 2, and so 62 problems related to this section. So only mechanics of, I believe mechanics of material is very, very important subject, and there are many, many subjects related to this. This is why probably I included too many problems, okay? And I needed to understand it. And I will look to this this distance x, y, it doesn't work for me. There's something amazing is not, but I will look at it and let you tomorrow where is the mistake. Let's look at the problem 617. A hollow shaft, a hollow circular shaft with an inner diameter is given, outer diameter is given, and a length of 2 feet is fixed from one end and subject to a torque from the other end. So basically we have the following scenario. Always try to draw a free body diagram, or as I call it, translate into English. So this is the torque that is applied here, which is, it is 1,000 pound foot or foot pound. And the inside radius and the outside radius. And the G is given. The maximum shear stress, tau max. Tau max is happening at the outer fibers, as we talked, that the shear stress is increasing linearly, where the shear stress here is 0. And since this is a hollow 0 up to here, but start to build up until we get the tau max. So the tau max is happening at the outer fibers. Okay, I need to check if this is a thin or thick. It turned out to be. So this is the J, polar moment of inertia. From where? From the NCEES on page 70. Oh, this is the one I'm referring to. Let me make sure that I copy the page. Page on page 70 of the NCEES. No, this is not correct. Okay, the J is given here. For this one here, it is on page 112. Page 112. Okay, probably this page was based on the older one because it was 2 columns. So page 112. 112. Yeah, page 112. So the J is given by this equation. Here it is, the one I was referring to, page 112. Okay, so you don't have to memorize. Is J is equal pi a to the 4th minus b to the 4th divided by 2, where a is the outside radius and b is the inside radius. So they're using a and b instead of using r, not to confuse with the radius of gyration. This is the reason they decided to do that. And here it is. So I plug it in and it turned out to be this. And tau max is equal to r divided by j. Which r did I use? I use the outer radius because this is the r in and this is the r out. Be careful, okay? So because they might give you an answer. If you use the inside radius, this will give you the minimum, not the maximum. So the keywords I hear, if the word is changed to be minimum, so I will use the inside radius. Okay? And maybe I have it here, probably. No, I don't have it, but it will be a good. So pay attention to keywords, as I mentioned before. Keyword or keywords. And this is the last problem I'm going to cover because I got so hungry and I'm going to go and eat. Okay? And some of you also need to break their fast in Ramadan. Some of you heard about Ramadan where we are fasting. So, and I will continue this tomorrow. I'm going to meet again with you tomorrow, guys. I added another session, by the way, I believe on the 15th. I will do all my best anytime I can find. Try to help. I'm trying to help everybody. I'm behind with some groups, but I will do everything to help everybody. Just pray for me to stay healthy, and I will keep doing my best. Problem 618 is asking for the angle of twist, which is phi. Phi is equal TL divided by JG. JG, okay? Or GJ, much better, okay, order. Okay, the polar moment of inertia is here. the same equation. And from where I get G, the shear modulus, he gave it to you. Assume, okay, the shear modulus is given. If it's not given, he should tell you what material is that, what kind of material, because we know in mechanics of materials, the table that I showed you more than once, okay? So this is, that has the G, and this is E, and this is Poisson's ratio, and this is alpha, the coefficient of thermal expansion, and this is rho, is density. Density, how many pounds per cubic inch. Okay, you know gamma, we are using rho or gamma density. For example, what is gamma steel? As I mentioned last time, probably, or time before, or we know gamma water, which is mentioned 62.4. Do you remember 62.4 pound per cubic foot? So if you have 1 cubic foot of water, this weighs 62.4 pounds. What do you think if you have 1 cubic, this is 1 foot, 1 foot, 1 foot. If you have 1 cubic foot of steel, do you think how much it weighs? 1 foot, 1 foot by 1 foot. Gamma steel. 62.4, this is water. How much is gamma steel? You have it here. Gamma steel is equal 0.282, but this is pound per cubic inch. So if you take 0.282, okay, this is inch cubed. This is pound per cubic inch. Inch cubed. But how many inch cubed in 1 cubic feet? It is 12 cubed per cubic feet. This is inch, which is 1728. If you multiplied 1728 times this number, normally we use gamma steel, by the way, the steel manual using 490 pounds per cubic foot. So the steel is 490. So it is point, let me see if we're getting close to 490 or 490, 491. Steel manual using 490. So it is 0.282 enter, 1728 times, I get 487.296. Okay, probably if they rounded more, probably will get the 490. So 487 is acceptable, and the rounding it will not. So this will give you 487, okay, 0.3 pound per cubic foot. So the density is given. So we need to know what is given to you for the exam. Okay, and I needed to, while I hope that you have a hard copy of this, you can write these things. You need to study while you are studying to know what is this, what is this, what is this, at this, and use mark. If we are going to see another table, which is average mechanical properties of typical engineering materials. Okay, he gave you gamma, pound per cubic inch. He gave you E. He gave you G. He gave you the yield, sigma Y, sigma U. This is sigma U, the ultimate strength, and this is sigma Y, which is the yield. He gave you the percent elongation in 2 inches. Poisson's ratio again, and the coefficient of thermal expansion. This is US units for different types of alloys here. So these tables are, this is gamma, by the way. These tables are useful, and we need to know what are included in this table. I will stop here, and I will see you tomorrow again, or you'll join me again tomorrow. So the last thing I need to mention, if G is not given, I will go and see table 1. Which table is that? That one has the G. Okay, see table 1 on page 138. See table 1, page 138. 138, that's correct, 138 of the NCEES. Okay, do your best, and I will stop here. So I still have only 2 calories left. Okay, 1 calorie will take me down to the stairs to my car, and 1 calorie will take me to home, and after that I will eat and I will see you tomorrow, guys. Enjoy the rest of your day. And I hope that you enjoyed the lecture. And I will look to this X. Why is not working for me? It seems that when I'm getting hungry, it seems to me things doesn't work for me very well. But I will do my best. Okay. Thank you very much for coming today. Stay safe, please. Okay. The virus is still available. Still alive. Okay. The virus is still alive. Don't take the risk, please. Okay. Because your health is very important. And thank you very much. Good night, everybody. Bye-bye.